Okay, so now we are looking at standard deviations, looking at modeling with normal distribution z-scores. So z-scores are basically how many standard deviations you are from the mean, the population mean, that letter mu. And it's one of the most common tools used in stats. If someone has any recollection, memory of their stats or data courses, they always remember the z-scores. It's just a really useful tool to analyze your data and determine how usual or unusual a data point is in relation to all your other data points. So we've talked about normal distribution. So standard normal distribution, the normal curve is not only bell-shaped curve, but it's the most useful one. A standard distribution is a normal curve with a mean of 0 and a standard deviation of 1. So if you look at this graph here below, you can see this normal with the n, 0, 1. You're looking at your mean and your variance or your standard deviation, and that is your normal curve. So that's basically our standard, regardless of what data you're looking at. The standard normal distribution is written as x n bracket 0, 1 squared. So remember the 0 is your mean, and this here is your variance, which is standard deviation squared. So you can always find the square root of that to find your standard deviation. So if I look at this example here, n5, 4, that would mean my mean is 5, my variance is 4, standard deviation would be the square root of that. And that would refer to a population that is normally distributed about a mean of 5 with a standard deviation of 2, which is the square root of 4. Each element of a normal distribution can be translated to the same place on a standard distribution by determining the number of standard deviations a data value is from the mean. That's called your z-score. So basically we are seeing how far our data point is in comparison to the normal distribution curve. So we're basically translating whatever data sets and observations we have onto this normal curve. That here is essentially your z-score. And if you look at the bottom of this lesson, you can even see these online. You see this lovely chart, and we'll show you how to use them. But these are essentially your most common basic z-scores. So I'll read through the steps here, and then hopefully it makes more sense once we actually do it. So z-scores. Once you have calculated the mean and standard deviation, z-scores, your standardized scores, which you saw in the chart, are used to compare values that have different means and standard deviations. Because we don't have a standard deviation of 0. We have whatever we measure. Remember, real life has a lot of variance. A z-score is the number of standard deviations a value is above or below the mean. So the score will tell you how many standard deviations I am above or below the mean. A positive z-score indicates the value is above the mean. A negative z-score indicates the value is below the mean. Okay, so 2 important points there. Also used to estimate how many other pieces of data in a population are above or below a given data value. So the formula that we use is z is equal to x minus x bar over the standard deviation. So your observation minus the mean divided by the standard deviation. So if I took x minus x bar, that's going to tell me how far away I am from the mean, but I want to know how many standard deviations I am away from the mean. So that's why we divide by the standard deviation. The value calculated using the formula and standardized using the z-score table. You don't have a textbook, so that's not relevant. You're going to the end of the lesson, and you have a chart there. You'll also see online there are, since we are online, there's a lot of, apps or websites that you can actually just type in your percentile or your z-score to figure out the number you're looking for, but you do need to understand how to use that chart as well. The z-score table ranges from negative 2.99 to 2.99. And if you recall, the reason because of that is anything outside that 3 standard deviations from the mean is considered an outlier, so that data is not relevant to us. Percentiles. A percentile is a data value that has a certain percent of the data less than it. Okay, so this is a key point here because you need to keep that in mind, the data less than it. Because that value is going to basically tell us, if I have a graph here, If this is my point here, it's going to tell me all the data that is less than. Okay, so all of that there. The median is the 50th percentile. Q1 is the 25th percentile, Q3 75th, that's all review. The kth percentile is the data value that is greater than the k percent of the population. So if a value is in the 70th percentile, then 70% of the population has a value less than or equal to this value. So if I say 70th percentile, that's basically, let's draw a little sketch here. If I said, like, say that's 50, say that's 70, everything less than that, okay? And that's calculated basically using your Z-score table, which is at the end of this lesson here. Okay, so let's do a couple of examples and I'll show you how to apply this. So for the distribution x equals n 14, 4 squared, our mean is 14 and our standard deviation is 2. I don't know why I wrote 4 there, but it's 2. So let's use our formula. So this is the mean. Standard deviation would be, oh, sorry, actually it's 4. That's why. Standard deviation is 4 because our variance is essentially 16. Okay, it's just the way it was written there, 4 squared. Your variance would be 16. The standard deviation would be 4. So Z is equal to, the formula is the observation minus the mean divided by the standard deviation. So the observation here, x is 10. Our mean is 14 divided by the standard deviation of 4. So negative 4 over 4 equals negative 1. So that means 10 lies 1 standard deviation. It's negative, so it's going to be below the mean. Okay, so again, think of your curve. This is my mean. We're at 1 standard deviation below. Okay, that's where 10 would be. Okay, so if I look at 32, same thing. Z equals observation of 32 minus my mean of 14 divided by my standard deviation of 4. You can always pause the videos to calculate this yourself. You get 18 over 4, which is equal to 4.5. So that means 32 is 4.5 standard deviations, it's positive, above the mean. 4.5 standard deviations, this would be an outlier. Okay, remember anything above or below 3 standard deviations is your outlier. So, Barb currently has a calculus mark of 84% in Miss Falconer's class. Her class average is 74 with a standard deviation of 8. Sandy has a mark of 83 in Miss Wences' class. The average in Sandy's class is 70% with a standard deviation of 9.8. Determine who has better marks using Z-scores. So we're going to do this separately. Remember your standard normal distribution, n is 0, 1. So let's look at Barb and compare her result to her class. So Barb has a Z-score of, her observation is 80, her average is 84. So her average is 84. The class average is 74, standard deviation of 8. So 84 minus 74 divided by a standard deviation of 8. That gives me 10 over 8, which is 1.25. So that's 1.25 standard deviations above the mean. Now let's look at Sandy. So Sandy has a mark of 83%. The average in Sandy's class is 70, standard deviation is 98. So Sandy's Z-score. Her average is 83, and we're comparing it to that class average, which is 70, so that's lower than Ms. Falconer's class. Standard deviation is 9.8. This here gives me 13 over 9.8, and that is 1.33. So that means Sandy is 1.33 standard deviations above the mean. So if you think of that curve, Sandy's higher up on that curve, meaning Sandy has the better mark. So let's write a little therefore statement. Therefore, Sandy's mark is 1.33 standard deviations above the mean. So she's closer to the top of that normal distribution curve and is doing better. Okay, so it's above the standardized mean. So while it looks like Barb has an 84 and Sandy has an 83 in comparison to the class and the other data points and the standard deviations there with that curve in each class, that gives you a standardized comparison. So just because somebody has an 84 in one class and someone has an 82 in the other class, and you're saying, well, hey, miss, that person has a better mark, why are they doing better in that class? It's all relative to the data points within that class. Okay, so that's the Z-score helps normalize that to create a fair playing ground comparison of how the marks are related to each. Okay. Now let's look at using this standard, the Z-score table. So we're going to find the percentile that corresponds to each of the following scores. So we have a Z-score here of 0.44. So you're going to look up 0.44 on chart. I'm going to show you how to do that. So if I go down to my chart, the first half are negatives. I need to go to the positives. So I'm at 0 here. And if I go down, I'm at 0.4, but I need to go over to 0.44. So the 0.44 would give me a percentile of 0.6700. So the percentile here would be is 0.6700. So a reminder, this is your chart. You have Z-scores along the top. You have Z-scores along the side. So you look at the first decimal. If you have a second decimal, look at the top. And then in the middle will be your percentiles. So you're going to do the same thing now, negative 0.83. So I'm just going to take out my highlighter. So negative 0.83. So I'm at negative 0.8. I have to go to negative 0.83. So this here would be negative 0.80, negative 0.81, negative 0.82, negative 0.83. So 0.2033. 0.233 is the percentile. Okay. Now we're going to go the other way. So using the Z-score table, find the Z-score that corresponds to each percentile. So we're looking for the Z-score. These here are percentiles. So it's a little bit more, I guess, tricky in a way. We now have to look at a lot more numbers because we're looking for, actually let me write this out as a decimal, the 45th percentile. 45th percentile is 0.4500. 90th percentile is 0.9800. So you have to look in the middle of the chart, which are a lot more numbers, for the 0.4500. It's sometimes you'll find the exact number. Sometimes you're going to have to look for two numbers. So let's look at what we have here. So I'm looking at 0.4500. If I look at these positives, these are all too high. So I'm going to have to look somewhere in the negatives. You can see, I'll just kind of use this, negative 0.45, we somewhere in this range. Okay. So if I look, negative 0.412, if I keep looking, let's look here. So I have negative 0.12, maybe. This one would be 1. And this probably would be close enough as well. So I can use these two, because other ones are a little bit further apart. There's no 0.45, so I have actually two values, negative 0.12, negative 0.13. So what you do then is take the average of negative 0.12 or negative 0.13. You can take the average of both. Negative 0.12 plus negative 0.13 divided by 2 gives you negative 0.125. Okay, that's your Z-score. The 98th percentile, so I need 0.98. So if I look, negative 0.98, would be, I would say here. Let's just check what number this is at. Negative 2, Z-score of 2.05, I'd say. That one there. Negative 9.798. So that's close enough to negative, 0.9800. So you have a Z-score here of 2.05. You want to take the number, the Z-score that's as close as possible to that percentile. So now we have another example here. Perch in a lake have a mean of 20 centimeters and a standard deviation of 5. So a mean of 20 centimeters, standard deviation of 5. Find the percent of the population that is less than 22 centimeters. So we're going to use our Z-score. My observation is 22. And remember, the less than is what I was talking about here above. It's showing less than. Okay? The percentiles show less than, so keep that in mind when we get to part C. So 22 minus 20 divided by the standard deviation of 5 gives us 2 over 5. And you can, again, pause the video, do this on your own. Gives you 0.4. You're going to look up in the chart. This is not your answer, right? This is your Z-score. So we're looking up in the chart, 0.4. So 0.4 gives us this number here. So 0.6554 is a percentile. So the percentile is equal to 0.6554. Remember, this percentile tells me everything less than 22. So that means 66% of the population is less than 22 centimeters. Okay, so now let's look at the same thing. Z-score here, we're looking at less than 16. So a reminder, this is my normal curve. This is my mean. We're looking at less than 16. So if 16 is about here because my mean is about 20, I'm looking at what is the area under the curve going that way. Okay, it's less than. So my Z-score is 16 minus 20 divided by a standard deviation of 5 And that gives me negative 4 over 5, which gives me negative 0.8. That is my z-score. You're going to look up the percentile. So we're at negative 0.8, negative 0.8, and that gives you 0.211 percentile. Therefore, you can say about 21% of the population is less than 16 centimeters. And now this is where you want to keep this in mind. We're now looking at greater than. All these scores tells us a percentile less than. So let's first just figure out what we have here. So we have a z-score of 25 minus 20 over a standard deviation of 5, which gives us 5 over 5, which is equal to 1. So if I look here, this is my mean of 20. I am looking for greater than 25. So everything above this point. I want to find out what that is. This one, though, we're going to have to look at a complementary. So if I look at 1.0 gives me 8.413. So that means my percentile is equal to 0.8413. That number is telling me all of this area. It's telling me less than. I want to find out greater than, so we're going to look at a complementary set. So if I take 1, because we know the area under a normal distribution curve is 1, minus 0.8413, that gives me 0.16. So that means this area is actually equal to 0.16. So therefore 16% of the population is greater than 25 centimeters. Okay, so keep in mind the less than, greater than, and visualize that graph. And our last example here. So the last example is the number of red blood cells in millions per cubic microliters is normally distributed with a mean of 4.8, standard deviation of 0.3. So we know it's normally distributed. We have a mean of 4.8, standard deviation of 0.3. We're going to find what percent of people have a red blood cell of less than 4. Less than 4. So remember, this is our curve. We're looking at less than 4. So let's find out, that's my observation. 4 minus the mean of 4.8 divided by the standard deviation of 0.3 is equal to negative 0.8 divided by 3, negative 2.67. So remember, that's my z-score. That's not my percentile. You're going to go down to your chart. Negative 2.6. Negative 2.6 is here. 2.67 would be here. So 0.038. So my percentile is equal to 0.0038. So that's below. Okay, so remember, this is negative 2.7. Basically, I'm looking at everything below. So therefore, we can multiply this by 100 and get a percent of 0.38% of people have a red blood cell count of less than 4. Now we're looking at what percent have a count between 4.7 and 5. So basically, I need to look at I'll do this a visual. My mean is 4.8. We have 5 and 4.7. Those are not drawn to scale. I have to look at I'm trying to find how many people are between here. So if I find out this area and this entire area and subtract the 2, it'll give me the area between. So first, let's find out our z-score for 4.7 divided by our standard deviation. And this gives me a z1, let's say, of negative 0.33. So we're going to find out what the percentile is for that. So negative 0.33. Different color here. Negative 0.3 is there. Negative 0.33 would take me to 0.3707. Negative it's positive. 0.3707. So this here has an area under the curve of 0.3707. Now let's find out the z-score for the second part, which is 5 minus 4.8 divided by 0.3. And that gives me a z-score for this part of 0.67. So let's go down, 0.67. Yes, I said 67, 0.6. 0.7486. 0.7486. So here, this is 0.7486. So if I take, what's the best way to draw this? If I have this area and I subtract this area, it's going to give me this middle part, what's left. Okay, so if I have all that blue, I know it's a whole lot of scribbling, but trying to visualize the colors there, all that blue minus that orange will give me this pink. So now we can look at the difference. So that's actually I don't want to do that there. 0.7486 minus 0.3707, that gives me 0.38. So therefore, 38% of people have a count between 4.7 and 5. Okay. And the last part here. So what count would someone need to have to be in the top 5%? So now we're looking at percentiles. Okay, so this here is your percentile of 5%. So the first thing you need to think about is kind of work backwards. Top 5%, normal curve here. Top 5% would be 5% would be 0.05, basically 0.05. This is where you have to remember the greater than and less than. So if I want to be in the top 5%, top, so that's above 5%, you need to find basically the 95%, because that's going to tell you what's below to find what's above. So 95% is basically 0.9500 as a percentile. Part 2, so that's part 1. So we're going to find the z-score for 0.9500. So this is 0.95. 0.95. So we could be looking at here at 0.9484. And I could also look at 0.9495. Those are both close to 0.95. You could also potentially look at 0.9505. Okay, so you could also look at here. So let's use just the average between the two for this purpose. So I have 1.64 plus 1.65 divided by 2. That gives me 1.645 as a z-score. So now for part 3, we know, let's write out the formula. They're asking what count I would need. So what's the observation that I need to have? I know the z-score is about 1.645. You could also use the 1.66. Should give you something still similar. I don't know this observation. That's what I'm trying to find. Minus 4.8 divided by my standard deviation of 0.3. We're going to multiply. So that gives me, what do I have here? 1.645. Yeah, so 0.4935 equals x minus 4.8. You're going to add 4.8 to each side, and you should get x being 5.292. So basically, you would need an RBC count, red blood cell count, of at least 5.3 to be in the top 5%. Okay, because we know that that's like our threshold here. Okay, this here, 5.292 would be at that point there to be in the top 5%. Okay, and you have textbook questions to work on this. The more you practice it, the more you'll understand the difference. Just be aware between the percentiles, the z-scores, your observations, and standard deviations.